Hello Geometry, we are on day 2 of section 7-6, Dilations and Similarity in the Coordinate Plane. Excuse my sniffly nose, I'm going to sound a little plugged up here. Anyway, yesterday we were applying similarity properties, and today we're going to use coordinate proofs to prove figures similar. So I left most of the notes open for you so that you could just kind of follow through. So let's move to the second day of 7-6. Okay, you could go and watch a couple of videos, as you see here, that are available with Holt-McDougall online, proving triangle similar. But let's also try it here together, and we can walk through a couple of samples that are in your notes right here. If you're given coordinates as you are here, what could you do? Well, you could certainly plot them. So you'll see in your notes that we have the image of triangle EHJ. Let's see where that is. EHJ, so it's like the large triangle, right? And we're told that it's similar to EFG, EFG here. Okay, and so that is the case after having plotted all of the given points. So if we were going to prove that these two triangles were similar, what would we have to do? Yeah, we would have to show that we have proportional sides, corresponding sides. We could also prove something about their angles, that they have all congruent angles, right? And then that would also prove similarities. So we certainly have the ability to look at the sides. And how do we do that? What formula do we use to find these lengths? You got it, it's the distance formula, right? So as they state here, first you can plot them in a coordinate plane, and then we can use a distance formula to find the various sides. So we want to find EH, also EJ is this other side, and HJ, and notice that they actually are focusing on EH and comparing it to the corresponding side EF, and then EJ, and we can compare that to the corresponding side EG, right? And so again, we find the difference in the x's and the y's squared. We're using our Pythagorean there, really, right? And we take the square root and we find these lengths. So the next thing we would do is set up our proportions to see if EH to EF is equal to the ratio of EJ to EG. Or we could flip those upside down, right? There are a number of ways that we could look at them. And indeed, they look at EH to EF and EJ to EF. And we find that when we substitute the known distances, the known lengths, we have a ratio of 2 in both cases. So we can say, since this proportion equals this proportion, angle E must be congruent to angle E. We also know that angle EHJ is congruent to EFJ, EHJ to EFJ, G. And so by SAS, we have our SAS similarity theorem. Very good. Okay. So in this next example 4, we're using the SSS similarity theorem. We're going to graph the image of ABC after a dilation with a scale factor of 2/3, and then verify that ABC prime is similar to the original ABC. So how do we dilate an image, or a pre-image, the original here? We multiply each of the coordinates of each vertex by the factor, right? And that is what we see in our next slide. So each of the coordinates has been multiplied by the dilation factor, and we end up with the new coordinates for the new vertices of ABC prime. And we can show that by graphing it, so you'll want to use graph paper today to do this. And here we have the original and the enlargement by dilation. Again, the factor was, oops, I'm sorry, it's a reduction, 2/3. We have the original, and then in the red, we have a reduction, don't we, of 2/3. It's actually shrunk, hasn't it? And so there we have an image. So if we're going to show now that they are similar, we're going to compare their corresponding sides. And we once again do that by looking at using our distance formula to find the lengths of these sides. Okay? And in this example, we were asked, or we were told that we were going to be using the SSS similarity theorem, so we will want to find the lengths of all three sides. We'll compare AB to A prime B prime, and BC to B prime C prime, and CA to C prime A prime. So we'll compare all three sides. So we do that again with our distance formula, right? So here we have the length of AB, BC, and AC, and there we have AB prime, BC prime, and AC prime. So when we set up our proportions, do we prove similarity? Let's see. AB prime to AB equals 2/3. The square roots of 2 just cancel, don't they? BC prime to BC also equals 2/3. And finally, AC prime to AC, again, equals the ratio 2/3. So these ratios are equivalent. Therefore, triangle ABC is similar to ABC prime by the SSS similarity theorem. Okay. Okay, so you're ready to dive in and get going with your work. Before you do, why don't you try one completely on your own? You're going to prove that triangle ABC is similar to triangle DEF given these points. Please be sure you slow yourself down and try this one out, and come back and check your work, and then you're on your way. Okay, I hope you plotted these. Could you find the distances without plotting? Yes, you could, and you could still set up your proportions. It's true. And when we do, we see that the proportions equal 1/2. And the alternative would be if you would set this up upside down, you would have a proportion of 2:1. Either way, we have triangle ABC is similar to triangle DEF, again by the SSS similarity theorem. And here you go. And again, don't go too fast. Work steadily, check your work, and do your best job. Good job.